U.S. Physics Olympiad Year 2025 F = MA. I offer private tutoring for Physics Olympiad preparation. I currently have openings. There is discount for group classes. Message me if interested. My email is fred1996@hotmail.com. Solutions for all problems can be found at the link in the description under this video. Problem number 1. A particle is moving on a plane at a constant speed of 1 meter per second, but not necessarily in a straight line. Which of the following plot pairs could describe the particle's position over time, in rectilinear coordinates? Solution for problem number 1. All three plots describe the particle moving at a constant speed. In plot 1, the particle is moving in a circle of radius 10 meters, and traversing the full circle in 10 seconds, so its speed is approximately 6.3 meters per second. In plot 2, the particle moves at a constant speed of square root from 0.8 square plus 0.6 square, which is 1 meter per second. In plot 3, the particle moves at a constant speed of square root from 0.5 square plus negative 0.5 square, which is less than 1 meter per second. So the answer is B. That was solution for problem 1. Problem number 2 and 3. The following information applies to problems 2 and 3. 3 identical disks are placed on a frictionless table. Initially, 2 of the disks are at rest and in contact with each other. The third disk is launched with speed v directly toward the midpoint of the 2 stationary disks along a path perpendicular to the line connecting their centers, as shown in the diagram. Analyze the motion of the disks after the collision, assuming all interactions are perfectly elastic and that when the disks collide, there is no friction or inelastic energy loss. Problem 2. Assume that all 3 disks collide simultaneously. What is the final velocity of the third disk? Solution for problem number 2. By symmetry, the third disk continues to move along the same axis. The first 2 disks experience only a normal force from the third disk, which is at an angle 30 degrees to the third disk's original velocity. Thus, if the third disk has final velocity vf, and the other 2 disks have final speed u, conservation of energy gives v square equal vf square plus 2u square. And conservation of momentum gives v equal vf plus square root 3u. Solving the system gives vf equal negative v over 5 and u equal 2 root 3 over 5v. This is the answer D. And that was solution for problem 2. Problem number 3. Assume that there is a little imperfection in disk's initial alignment, so when the disks collide 2 collisions happen one at a time, rather than all 3 disks colliding simultaneously. What is the final speed of the third disk? Solution for problem number 3. After the first collision, the disk that was at rest gains speed v1 equal v cosine 30 degrees and the third disk has speed v3 equal v sine 30 degrees, in the direction that's perpendicular to the line between the disk centers. The component of the first disk's velocity along the line connecting their centers is transferred to the second disk. The perpendicular component is unaffected. The third disk is now moving in a direction that's 60 degrees off from the line connecting its center with the center of the disk that's still at rest, second disk, so after the second collision, disk that was at rest will gain speed of v cosine 30 degrees sine 30 degrees and the third disk will have speed v3 equal v sine square 30 degrees, which is v over 4. This is answer 3 and that was solution for problem number 3. Problem number 4. A mouse M is running from A to a prime with constant speed u1. A cat C is chasing the mouse with constant speed u2 and direction always toward the mouse. At a certain time MC perpendicular to AA prime and the length of MC equal L. What is the magnitude of the acceleration of the cat C? Solution for problem number 4. For small angles delta theta we have next diagram. On this diagram acceleration A equal delta u over delta t. But delta u equal u2 delta theta. And delta theta over delta t is angular speed omega of point M around point C, which is just u1 over big L. Finally we have acceleration A equal u2 u1 over L, which is answer C. That was solution for problem 4. Problem number 5. 3 identical cylinders are used in this setup. 2 of them are placed side by side on a horizontal surface, with a negligible distance between their surfaces so they do not touch. The third identical cylinder is placed on top of the first 2, such that their centers form an equilateral triangle, as shown in the figure below. The coefficients of friction are μ1, the coefficient of friction between the cylinders, and μ2, the coefficient of friction between the cylinders and the ground. For which of the following pairs, μ1, μ2, will the system remain in equilibrium? Solution for problem number 5. From the force analysis diagrams and symmetry, we get a system of 4 equations in order to balance all forces and torques. There is normal force N1 between cylinders and normal force N2 between cylinders and the ground. There is force of friction F1 between cylinders and force of friction F2 between cylinders and the ground. The first equation we can get from total weight acting on cylinders from the ground. The second equation we can get from the projection of force of friction F1 and normal force N1 on the vertical axis. The third equation is projection of friction forces F1, F2, and normal force N1 on the horizontal axis. The equation 4 we will get from total torques acting on the cylinders from friction forces F1 and F2. Solving this system we will get results for all 4 unknowns. Requiring F1 less or equal μ1 N1 and F2 less or equal μ2 N2 implies conditions for μ1 and μ2. μ1 is good for pairs 1 and 2. μ2 is good for pairs 2 and 3. So the correct answer pair 2, which is answer B. That was solution for problem 5. Problem number 6. A ball rolls without slipping down a ramp, which turns horizontal at the bottom. At the bottom of the ramp, the ball falls through the air, as in the diagram. If the ball starts from the position marked O, it lands 10 centimeters away from the bottom of the ramp. Which starting position will get the ball to land closest, to 25 centimeters away? Solution for problem 6. The kinetic energy of the ball at the bottom of the slide is proportional to the height drop down the slide, so the horizontal velocity is proportional to the square root of the height drop. The time to fall is constant, so we need the velocity to scale up by 2.5, which means the height drop has to scale up by 6.25. This is choice A. That was solution for problem 6. Problem number 7. A mechanism consists of 3 point masses, each of mass m, connected by 2 massless rods of length L and a torsion spring acting as a hinge. The potential energy of the torsion spring is given by Us. This system is designed to walk down a set of stairs, as shown in the figure. The angles θ1 and θ2, see figure, represent the orientation of the rods, and their rates of change, ω1 and ω2, are the corresponding angular velocities. Assume that the mass on the surface is instantaneously at rest, which equation correctly describes the total energy of the system. Solution for problem number 7. Using expressions for velocities and positions, we set up the energy as a sum of kinetic energy, gravitational potential energy, and torsional potential energy terms. Velocities in x and y directions we may represent in expressions 1 and 2. So the total energy E will be expression 3. After calculations we have expression 4. Which is answer C. That was solution for problem number 7. Problem number 8. a symmetric spinning top, rotating clockwise at an angular frequency omega, is placed upright in the center of a frictionless circular plate. The plate then begins to rotate counterclockwise at a constant angular velocity omega. Assume the top's axis remains perfectly vertical and stable without any precession. From the perspective of an observer rotating with the plate, how does the top appear to rotate? Solution for problem number 8. When the plate begins to rotate, it does not exert any torque on the spinning top as the plate is frictionless, thus there are no external forces acting on the top that could change its angular momentum. As a result, the top's angular velocity in the lab frame remains unchanged. From the perspective of an observer who is rotating along with the plate at angular velocity omega, the apparent angular velocity of the top is given by the transformation omega top rotating equals omega top inertial minus omega plate. Plugging in the frequencies we have omega top rotating equals negative omega minus omega, which negative 2 omega. Since the negative sign indicates clockwise rotation, the observer on the rotating plate perceives the top to be spinning in the clockwise direction at twice its original frequency. This is the choice C. And that was solution for problem 8. Problem number 9. N circles in a plane, CI each rotate with frequency omega relative to an inertial frame. The center of C1 is fixed in the inertial frame, and the center of CI is fixed on CI-1, for I equal 2, etc. till n, as shown in the figure. Each circle has radius Ri equals lambda Ri-1, where 0 less than lambda less than 1. A mass is fixed on Cn. The position of the mass, relative to the center of C1 is R as function of t. For the n equals 4 case shown, which of the following statements is true? During the time interval from 0 to 2 pi over omega, the magnitude of acceleration of mass on C4 is 1 of 5. Solution for problem number 9. The orbit angular velocity and the rotation velocity are the same, which means it will always have the same phase, similar to Moon and Earth, where the Moon always faces the same way relative to Earth. Therefore, the entire structure actually rotates as a rigid body, and the mass is simply moving in a circle, at constant speed. This is the answer E, and what was solution for problem 9. The following information applies to problems 10 and 11. When two objects of very different masses collide, it is difficult to transfer a substantial fraction of the energy of one to the other. Consider two objects, of mass small m and big M much greater than small m. Problem 10. If the lighter object is initially at rest, and the heavier object collides elastically with it, what is the approximate maximum fraction of the heavier object's kinetic energy that could be transferred to the lighter object? Solution for problem number 10. Let the heavier object have initial speed v. It means that its kinetic energy E0 equal 1/2 of big M v square. In such an elastic collision, the final speed of the light object is approximately 2v, so its kinetic energy E is 1/2 small m 2v square. Thus maximum fraction E over E0 is approximately 4 small m over big M. Which is answer C. That was solution for problem 10. Problem 11. Now suppose that instead, the heavier object is initially at rest, and the lighter object collides elastically with it. What is the approximate maximum fraction of the lighter object's kinetic energy that could be transferred to the heavier object? Solution for problem number 11. Let the lighter object have initial speed v. So the total kinetic energy E0 of this object is 1/2 small m v square. Since big M much greater than small m, its final speed is also approximately v, but the direction of the velocity is reversed, so the impulse given to the heavier object is about 2 small mv. Then the kinetic energy E of the heavier object is p square over 2 big M, which is approximately 2 small m square v square over big M. Thus maximum fraction E over E0 is approximately 4 small m over big M, which is answer C. That was solution for problem 11. Problem number 12. A 50 grams piece of clay is thrown horizontally with a velocity of 20 meters per second, striking the bob of a stationary pendulum with length L equals 1 meter and a bob mass of 200 grams. Upon impact, the clay sticks to the pendulum weight and the pendulum starts to swing. What is the maximum change in angle of the pendulum? Solution for problem number 12. Use the equation for inelastic collision small mv equals small m plus big mu to get the velocity of the bob is 4 meters per second. Then use energy conservation H equals u square over 2g to get the height of 0.8 m. From there it is just trigonometry to get the angle theta equal arc cosine 1/5. This is answer A, and that was solution for problem 12. The following information applies to problems 13 and 14. Angela the puppy loves chasing tennis balls, so her owners built a tennis ball launcher. It fires balls along the floor at some initial speed, applying no rotation to them. The balls initially slip along the floor, then start rolling without slipping. Ignore the potential deformation of the ball and floor during this process, as well as air resistance. Problem 13. Which of the following plot pairs could show the linear speed v and rotational speed omega of one of the balls, over time? Assume the floor has a constant roughness. Solution for problem 13. As the ball is rolling while slipping, the friction force acts to reduce its linear momentum and to increase its angular momentum. The change in the angular momentum is proportional to the change in the linear momentum. The ratio depends only on the moment of inertia of the ball. The friction force will be constant until it drops to zero. This means that the plot of the linear speed should decrease linearly until it hits a constant level, and the plot of the rotational speed should increase linearly until it hits a constant level at the same time. This is answer A, and that was solution for problem 13. Problem 14. There are 3 kinds of balls that can be launched in this setup, all having the same radius r. First, a regular tennis ball, a thin spherical shell of rubber, of mass m1. Second, a solid wooden ball of mass m2. Third, a solid rubber ball of mass m3, where m1 less than m2 less than m3. All 3 types of ball emerge from the launcher with the same velocity. For which ball will the final velocity be highest? Solution for problem 14. The frictional force provides a linear deceleration of delta V over delta T equal negative mu g, where mu is the coefficient of friction. It provides an angular acceleration of delta omega over delta T equal mu g r m over I, where m is the mass of the ball and I is its moment of inertia. We're waiting until omega r equal V, which means that we care about delta omega r over delta T equal mu g m r square over I. The quantity, m r square over I, is larger for objects where the mass is close to the axis than for objects where it is far away, so it is larger for a solid ball than for a spherical shell. This means that the solid balls will pick up angular velocity faster and will end up with a larger speed at the time when the ball stops slipping. It means that balls 2 and 3 have the same final speed, which is greater than for ball 1. This is answer D, and that was solution for problem 14. Problem number 15. A uniform rigid rod of mass m and length 2L is attached to a massless rod of length L, which is fixed at one end to the ceiling and free to rotate in a vertical plane. The massive rod is connected to the free end of the massless rod. Suppose an impulse J is applied horizontally to the bottom of the massive rod. Determine the relationship between the magnitudes of the angular velocity omega small of the massless rod and omega capital of the massive rod immediately after the impulse is applied. The moment of inertia of a uniform rod of length d and mass m about its center of mass is given by I equal 1 over 12 mv square. Solution for problem 15. We need to find the speed v of center of rotation and angular speed omega of rotation. This just after the impulse. The speed we can find from the formula mv equal j. So v equal j over m. Angular speed from the formula 1/3 ml square omega equal jl. So omega equal 3j over ml. Now we can find the linear speed of the upper end of the heavy rod, which is simultaneously lower end of the massless rod. That will be v1 equal v minus omega l, which is negative 2j over m. It means that angular speed of the heavy rod is counterclockwise and weightless is clockwise. And omega equal v1 over l, which is 2j over ml. Finally, big omega over small omega equal 3 over 2. That was answer E, and that was solution for problem 15. Problem number 16. Two soap bubbles of radii are 1 equals 1 centimeter and are 2 equals 2 centimeters conjoined together in the air, such that a narrow bridge forms between them. Assuming the system starts in equilibrium, the bubbles are extremely thin, and that air can flow freely between the bubbles through the bridge. Describe the evolution and final state of the bubbles. Solution to problem 16. The larger the radius of curvature of a bubble, the lower the pressure inside it. So the pressure inside the smaller bubble is greater than the pressure inside the larger one. As a result, air will flow from the smaller bubble to the larger one. The smaller bubble will shrink and eventually collapse, while the larger bubble will grow. That was the answer A, and that was the solution to problem 16. Problem 17. A particle of mass m moves in the xy plane with potential energy, u as function xy equal negative kx square plus y square over 2, the closest point to the origin x equals 0 and y equals 0 during its motion was at a distance d, and the particle's speed at that point was v naught equals 0. Which of the following statements is true regarding the path of the particle, after a long time t much greater than d over v? Solution to problem 17. Unlike the spring potential, here we have a minus sign in the potential expression. The corresponding force is directed radially outward, with a magnitude proportional to the distance from the origin. Under the action of such a force, the particles will be pushed to infinity. Note that the force does not provide a torque about the origin. Conservation of angular momentum means that the angular momentum of the particles will be the same as at time 0, that is, the tangential component of the velocity will be inversely proportional to the distance from the origin and will tend to 0 at infinity, while the radial component of the velocity will increase as the particle moves away. This means that the direction of the particle's velocity will asymptotically approach a straight line from the center. Of all the answer options, this corresponds only to answer B. For an exact solution, let the initial position of the particle be d0, and the velocity 0v. The equations of motion can be written as follows. Here omega squared is equal to k divided by m. These equations give us the following solutions. Substituting the initial conditions, we have a plus b equals d, c plus d equals 0. Next, omega a minus omega b equals 0. Omega c minus omega d equals v. Solving this system, we have a equals b equals d divided by 2. C equals minus d equals v divided by 2 omega. Thus, we obtain the following solution. In the long run, the positive exponential term will dominate, and the particle's trajectory will be asymptotic to a line passing through the origin with slope v divided by d omega. Note that the positive exponential term cannot be equal to 0, since the particle had a point of closest approach to the origin. This is the answer B, and this was the solution to problem 17. Problem 18. A particle of mass m moves in the xy plane with potential energy uxy equals kxy over 2. If the particle begins at the origin, then it is possible to displace it slightly in some direction, so that the particle subsequently oscillates periodically. What is the period of this motion? Solution to problem 18. The potential function has a saddle shape, and the direction that allows simple harmonic motion is the displacement along the line y equals x. All other directions cause the particle to deflect toward the line y equals negative x. Suppose the particle is displaced a distance L along this line. Then x equals y equals L divided by the square root of 2. Therefore, the potential energy is ca L squared divided by 4. In other words, the potential energy is the same as that of a spring with stiffness ca divided by 2. So the angular frequency omega is equal to the square root of k over 2m. And the period will be 2 pi multiplied by the square root of 2m over k. This is the answer D. And that was the solution to problem 18. Problem 19. Near the ground, wind speed can be modeled as proportional to height above the ground. This is a reasonable assumption for small heights. A wind turbine converts a constant fraction of the available kinetic energy into electricity. The conditions are such that when operating at 10 meters above the ground, the turbine delivers 15 kilowatts of power. How much power would the same windmill deliver if it were operating at 20 meters above the ground? Solution to problem 19. By assumption, at 20 meters, the wind speed will be doubled. We're asked to find how the power of the turbine scales with wind speed. The energy that's available to be extracted over a small time interval is the product of the mass of air that flows past the turbine, and the mass density of the kinetic energy of the air. The mass of air scales as V, and the kinetic energy per unit mass scales as V square, so the total scales as V cube. Finally, because speed is doubled, the power B cube of 2, which is 8 times. That will be answer E. And that was solution to problem 19. Problem 20. The International Space Station orbits the Earth in a circular orbit 400 kilometers above the surface, and a full revolution takes 93 minutes. An astronaut on a spacewalk neglects safety precautions and tosses away a spanner at a speed of 1 meter per second directly towards the Earth. You may assume that the Earth is a sphere of uniform density. At which of the following 5 times will the spanner be closest to the astronaut? Solution to problem 20. The spanner will, of course, also orbit the Earth, in a slightly different orbit from that of the ISS. The total energy of the spanner is increased by this tossing maneuver, so its orbital period will be very slightly longer than that of the ISS. After exactly 1 orbital period of the ISS, the spanner will be very slightly behind the ISS on its trajectory. At other points along the orbit, the spanner and the astronaut will be farther apart. Because the spanner was tossed inward, its initial angular velocity will be slightly higher than that of the astronaut, i.e. it will pull ahead in its orbit. At the point where the spanner's and the ISS's trajectories cross for the first time, approximately halfway around the orbit, the spanner's angular position will be maximally ahead of the ISS's. Over the second half of the orbit, the ISS's angular position is catching up to that of the spanner, and it very nearly catches up by the time they pass through the point where the astronaut first tossed it. Let us now estimate quantitatively the lag of the wrench after 1 revolution. the initial energy of the wrench switch in a circular orbit was according to Formula 1. Here v0, the orbital velocity of the ISS, the astronaut and the switch, r is the radius of the ISS orbit and respectively a0 is the major axis of the station's orbit. Accordingly, Formula 2 is valid. After throwing the key of the main motion of the station, the total power of the key began to obey Formula 3, which after reduction turns into 4. For simplicity of calculation, we put v0 equal to 10,000 meters per second. Thus, the total relative increase in the major semi-axis, it will be 2 times 10 to the power negative 8, Formula 5. Next, using the proportion of the sixth, third Kepler's law, it turns out delta t divided by t is equal to 3 times 10 to the power negative 8. Ultimately, we get a lag of the switch from the station equal to 1.6 meters, and time a little more than 93 minutes. This will be the answer C. And this was the solution to problem 20. The following information applies to problems 21 and 22. Water flows through a pipe with a radius of 5 cm at a velocity of 10 cm per second before entering a narrower section of pipe with a radius of 2.5 cm. Problem 21. What is the difference in the speed of water between the two pipes? Solution to problem 21. We assume that water is incompressible. Therefore, A1V1 is equal to A2V2. Here, A1 and A2 are the cross-sectional areas related as squares of the radii. Then V2 will be 40 centimeters per second. And the difference V2 minus V1 will be 30 centimeters per second. This is answer B. And this is the solution to problem 21. Problem 22. To measure this difference, 2 graduated cylinders are connected to the top of the pipe, one in the broad section and the other in the narrowed section. Water then flows up each pipe and the height the water reaches is measured. Estimate the difference in height between the 2 cylinders. Solution to problem 22. Using Bernoulli's law we have equation 1. Hence the height difference will be as in the expression 2 or 7.5 millimeters. This is the answer B. And this is the solution to problem 22. Problem 23. The student conducted an experiment to determine the spring constant of a spring using a ruler and 2 different weighing scales. The measured elongation of the spring was 1.5 centimeters, and the smallest division on the ruler was 1 millimeter. The mass of the attached weight was measured using 2 different scales in the school laboratory, yielding values of 198 gram and 210 gram. The student also found that the local acceleration, due to gravity in her city is given as 9.806 plus or minus 0.001 meters per second square. Calculate the percent error in measuring the spring constant. Solution to problem 23. The relative measurement error of the spring stiffness is calculated as the root mean square measurement error of all 3 independent parameters. The length of the spring, the mass of the load, and the acceleration of gravity. Since K is equal to mg divided by L, we have a simple formula. Here delta L is the measurement error of the ruler, that is, 0.5 millimeters. The measured length L is 1.5 centimeters, delta M is the measurement error of the mass will be the difference in mass in half, and the mass M is calculated as the arithmetic mean of 2 measurements. And for G, we have an error of 0.001 meters per second squared, and G itself is 10 meters per second squared. As a result of simple calculations, we obtain a relative error of 0.044, which is closest to the answer B. This was the solution to problem 23. Problem 24. a massive bead is attached to the end of a massless rigid rod of length L. The other end of the rod is attached to an ideal pivot, which allows it to rotate frictionlessly in any direction. The rod is initially at angle theta to the horizontal, and there is no gravitational force. Next, the bead receives an impulse directly into the page, giving it a speed v. How long does it take for the bead to return to its original position? Solution to problem 24. No matter what theta is, the bead always moves in a circle of radius L. The total distance it has to travel is 2 pi L, so the time is 2 pi L over v. This is answer A. And that was solution to problem 24. Problem 25. A puck of mass m can slide on a frictionless inclined plane, prism. The prism has a much greater mass, compared to the puck, and is itself sliding without friction on a horizontal surface. The velocity of the prism is v equals square root from 2gh, where g is the acceleration due to gravity and h is the height from which the puck starts sliding on the prism. The transition from the prism to the horizontal surface is smooth. The puck starts from rest relative to the prism. Find the final velocity of the puck once it begins sliding on the horizontal surface. Solution of problem 25. This problem is easiest to solve in the initial rest system of the prism and the puck. Then, by conservation of momentum, we have expression 1. The mass of the puck m small multiplied by the final velocity of the puck v1 is equal to the mass of the prism m large multiplied by the final velocity of the prism. Further, by conservation of energy, we have expression 2. 1/2 m small by v1 square plus 1/2 m large v2 square is equal to mgh, which, by conditions, is equal to 1/2 of m small v squared. Solving these two equations with respect to v1, we obtain formula 3, that with small m much smaller relative to m large is equal to v. Going back to the original system, we obtain formula 4. The speed of the puck is equal to 2v. This is the answer E. And this was the solution to problem 25.